So here's something neat we can do with the mean value theorem. It's kind of in the background, but we'll bring it to the foreground later. Suppose you know a particular function value, and you know that the derivative is always greater than some value from kind of now, 3, on to some future time. What can you say about the function value at that later time? So pause the video, think about what you can say. All right. If we put this in terms of traveling, you could say, well, suppose I'm 20 miles away from a city at time 3 hours, and for until time 11 hours, I'm going to keep driving at least 4 miles an hour. Okay, this is kind of silly. What can I say about how far away from the city I am if I'm going away from the city by time 11? Well, you could say, well, I started 20 away. If I went as slow as possible while still staying true to the statement, I'd be driving exactly 4 miles an hour. For how many hours here? 8 hours, I think. So we could say, we could diagram it. We could say, here we are at time 3, here's time 11. Let's say you're here at time 20, here at 20 at time 3. So you know you're here. What can we say? Well, the slowest you could go is 4 miles an hour, and if you stayed exactly at 4 miles an hour, you would be doing a line like that. So let's say the slope is 4 miles per hour. So where would you end up? So this point would be what? 20 plus 4 miles an hour times 11 hours minus 3 hours, which I think boils down to 52. So would you be exactly there? Well, that's if you went as slow as possible while remaining true to the statement. Since you might have gone faster, you might have had a higher rate of change than that. Where can we say you ended up? Well, let's draw some possible curves of where you might have been. So go ahead and sketch in some possible curves here. Well, you might have done exactly that one. You might have done exactly that and then gone kind of faster. You might have gone kind of parallel like that. You might have gone faster and then kind of parallel. You might have gone like this and then kind of parallel. And what's true about all of those where we end up? Well, we could say they're all higher than that level. So f at time 11 is greater than or equal to 52. Can we draw some curves that would not follow this rule that f prime is bigger than 4, but look like they might? So we'll draw that same kind of line there. Suppose that slope is 4 still. Nothing special about 4, it's just a nice number. Could you say, how about that curve? Well, that slope here ends up not being as fast as 4, so you can't do that one. How about something like this? Nope, well, depends on how I drew that. There it levels off. Something that came up and went back down. So all of those are prohibited, even though they do end up bigger than 52. But also something that did that, or something that did that, those would also be prohibited. But these are all allowed because their slope is always at least parallel to the main slope here or taller. So we can form that. Does that expression look a little familiar? This plus that times this minus that. Is that a tangent line? What can we say? Well, it might be tangent, but we don't know that the slope here at our initial point is even 4. It could be 5 or 6 or 9 billion or something. So it's not necessarily a tangent line, but we could say it's a lower bound line. It's less than all the possibilities of functions that are allowed. So let's call it a lower bound line, which we could abbreviate LBL at x. So go ahead and write out what here, this is just a single computation, but write out a formula for what a line would be. it would be f of c plus, and then, so let's call this c. We can't say f prime exactly, but we could say whatever our lower bound on f prime is. Here 4 is a lower bound on f prime. Times x minus c. So we can use the lower bound line to say, well, the function value has to be at least this big. So we could say f of x is greater than or equal to that lower bound line on whatever interval that we're given information about. You could imagine the same sort of thing if we had information about f prime being less than or equal to something. Then you could have an upper bound line, let's say. And it would actually be the same formula. F of c plus whatever upper bound we have on f prime times x minus c. And then we would say f of x has to be less than or equal to that upper bound line. So let's relate this to the mean value theorem. What can we say from the mean value theorem? We know there is some no, I guess we're kind of confusing things here. The c here we meant to be our initial position, but in the mean value theorem we called this a and b, and c was somewhere in between. We'll go back to mean value theorem notation here. There's some position c in the interval a, b, so that I'm going to say f of b minus f of a. So I'm going to do the difference quotient first, is equal to f prime at c. So that's the mean value theorem, and we'll say if f is differentiable in a to b, and then what can we say about f prime of c? Well, if we have some bound on it, like f prime is always bigger than 4, let's just use the 4 as an example here. So let's say we were given that. So we know that f prime of c is equal to this, but f prime of c is also bigger than that. So we can write f of b minus f of a over b minus a. Just kind of skipping the part about f prime of c, we can just say that that's bigger than or equal to 4. And then if we solve that using algebra, multiply both sides by b minus a, add f of a to both sides. So f of b greater than or equal to f of a plus 4 times b minus a. So we're getting that kind of tangent line formula feeling to it. Here b is the end point, but you could also call it x if x is anywhere between a and b. So that's how we can use the mean value theorem to relate to this upper bound line, lower bound line kind of problem.